Hello, hello, hello. This video, we're going to talk about everything you should know about transformations. So, here's the topics we're going to go through. The first one, translations, dilation, and reflection. That's the three basic transformations we're going to learn. We're going to go through the definition, what they mean, and what does it do to the graphs. Later, we're going to go through the combination of the three basic transformation and how to find the equation of the graphs after all the transformations. After that, we're going to go through what if we are given the equation of graphs and we got to find the transformation that maps the original graph to the end result of the graph. Lastly, we're going to find image, which is the graphs after transformation, and determine the transformations using function notation, which is a quicker way compared to the method we learned from the basic definitions. Okay, let's go. First kind of transformation, we call that translation, and it's the most basic transformation we could have. Let's have a look at the examples. For example, I want to move a point called 1, 1. If I move it to the right by 3 units, it becomes 4, 1. Easy enough. So I want to move this point to the right by 3 units. So the x value actually increased by 3 because I move it to the right along x-axis. Now, second example, 2, 4. If I move it to the right by 3 units, it now becomes 5, 4. Easy. Another example, negative 1, 1. If I want to move it to the right by 3 units, it becomes 2, 1. Yep. And this is the foundation of transformation. Transformation does not just apply to a line, a smooth curve like a graph. It actually moves every single point. If we want a graph illustration of all these points, we can connect them. We can connect all the points. Say this 1, 1, 4, 1, and 1, negative 1, 1. These 3 points, they come from a graph called y equals to x squared. So if now I say I want to move the whole graph y equals to x squared to the right by 3 units, it actually means we're going to move every single point on y equals to x squared and form quite a few new points, which is marked as a cross on the graph, like those blue crosses. Then we connect all those coordinates being transformed and form a new graph. And now this graph is called y equals to x minus 3 bracket squared. This is the graph after I transform the original graph y equals to x squared by 3 units to the right. Or we can say, more formally, translate 3 units to the right, if that makes sense. Right. And the whole illustration on decimals actually want to tell you one important message, which is when we're moving graphs, we're basically moving all the points together to form the end product of the graph. Right. Now, the question becomes, how do I know I can find this end product called y equals x minus 3, whole thing, bracket squared? How can I find it mathematically or numerically without graphing it out on a graphing tool? Now, we're going to go through that by a method called mapping. This is something we call mapping. So this method comes from the definition of transformation. If we can manage a way to explain the transformation that apply to each single coordinate on the graph, we can then use that equation or use that relation to help us find the equation of the graph. Now, translations. If I translate h units in the positive direction of x-axis, which means to the right, now, this language is more formal. This is the formal language we use to describe a transformation. in the positive direction of x-axis. Simply speaking, we just call that move to the right. But if we want to express it more formally, we call that in the positive direction of x-axis. And k units in the positive direction in the y-axis. Same thing. Positive direction is to the right. Then if the original coordinate, we call that x comma y, the end result then becomes x plus h and y plus k. Sorry, this is y. Right, because I increase my x value by h and I increase my y value by k by this transformation, right? Now, if negative, if it's in negative direction, then we just make everything to minus. So negative direction of x-axis, x value has been decreased, and negative direction of y-axis, y value has been decreased as well. Okay. Now, this is how we express the transformation of coordinates. Notice that mapping method does not require you to move the graphs at all. You just try to describe the transformation that apply to the coordinate, and I'll tell you what to do next. Right. Now, after you identify the coordinate transformation, now we're going to write down some equations to describe it. For example, if we call the original coordinate x comma y, we're now not able to call the new coordinate x comma y again because x comma y has been used. They describe the original position. Then I have to use some new notation to describe my new position of the transformation. Then we use x dash and y dash. They indicate the position of my coordinate after transformation. X dash now equals to x plus h, y dash equals to y plus k. Right, because they are the new coordinate and we managed to describe the movement by some equations. Same thing applies to negative. Now you may wonder why it helps us to find the equation. I'll show you with an example. For example, for the equation of y equals to x squared, and we're going to perform a translation of 2 units in the positive direction of x-axis and 4 units in the positive direction of y-axis. Now the first step will be we write down the transformation in coordinate form. Originally, we call the coordinate x comma y. And if we move x in the positive direction, we increase the value of x by 2. If we move y in the positive direction, we increase the value by 4. Now, that's the coordinate after transformation. Okay? Then we're going to write down some equations. Equations now become, this is something we call the new x. We indicate that as x dash. This is the new y. We call that y dash. Okay? Now, x dash now equals to x plus 2. Y dash equals to y plus 4. Notice that these two pieces of information, they're useless right now because we don't have any information about them. We don't have information about x dash, y dash, but we do have the relation between x and y, which is the original function. Now, see what happens if I do some rearrangement to my equation. Now, if I rearrange to make x and y the subject, it will be very helpful. If we decrease, if we minus each side by 2, x now equals to x dash minus 2. This one I minus both sides by 4, y now equals to y dash minus 4. Now, we know that y equals to x squared. We also know that y equals to y dash minus 4 and x equals to x dash minus 2. We can now substitute. We got something like this. Y dash equal minus 4 equals to whole thing, that's in bracket, x dash minus 2, because we are replacing the x with the whole thing x dash minus 2, whole thing squared. Then we have y dash equals to x dash minus 2 whole thing squared plus 4. And see, this is the answer to the question. We're not moving the graphs. By some simple steps of moving coordinates, whatever graph you have in this question, it can be anything. It can be any graph. You just follow the same step, then worry about the graph in the end. And now, you may want to rewrite the equation to make it looks better. Y equals 2, x minus 2 squared plus 4. This is my answer. Because when you write an equation, you don't have to really tell that's new, that's old, that's old equation, that's new equation. You just use x and y to answer the question. So just rewrite in a fancy way. Okay. And this is the method what we call that mapping. And it applied to other transformations as well. Okay. All right, let's move on to another example. Please pause here and use up to 5 minutes to try to do this question yourself, then come back to check answers. All right. Now you have used 5 minutes to solve this problem. Please check answers now. So don't worry about the function itself. Don't worry about it. We just do the transformation to coordinate first. We have x, comma y, move. Translation of 3 units in the positive direction of x-axis. That means x increased by 3. And negative direction of y-axis. That means my y decreased by 2. Now, this is something we call x dash. This is something we call y dash. And x dash equals to x plus 3. Y dash equals to y minus 2. Then make x and y the subject. X equals to x dash minus 3. Y equals to y dash plus 2. So we can state the original function once again. Now, y just equals to fx. So we can just rewrite that into y equals to 1 over x form. Yeah, because we do need this y. This is so important for us. Now, replace the y with y dash plus 2. And replace the x by x squared. X dash minus 3 equals to x dash minus 3 and 1 over that. Then tidy up the equation. Y dash equals to 1 over x dash minus 3 minus 2. Then you can rewrite the equation. Answer the question, say, this is my final answer. Y equals to 1 over x minus 3 minus 2. And this is your final answer. All right. So this this method may be slower compared to some other method you learned before, say observation, or we call that inspection. By looking at the graph or the original equation, then perform the transformation on the equation itself, and every single step you're working on the equation. Now that kind of thing is quick, I have to admit that, but on the accuracy aspect, this method is much better because coordinate is very simple to use and it's very, very difficult to make a mistake on coordinate as long as you read the question carefully, right? This is very straightforward, easy to follow, and you can copy the same method over and over again for any kind of question. Then whatever equation you have, you just do it in the end. That will always be the last step to answer these kind of questions. Okay? And that's all you got to know for translations. Okay? Now, another two basic transformations we have, that's something we call dilation and reflection. Let's go through dilation first. Dilation. Now, dilation actually means you can imagine you are stretching or extending the graph. Now, there are two kind of dilation. One is dilation from x, one is dilation from y. Now, let's have a look at that one by one. For example, you have a graph. That's something we call y equals to square root of x. That's in red. Okay. Now, sometimes you want to stretch it by, for example, you want to dilate it from x-axis. This is the formal language, very formal dilation. fancy name, fancy term. If I explain it in a more straightforward way, dilate actually means stretch it. For example, from X, that means you're holding your hand on the X-axis and your dilation from it. Imagine there's the X-axis between my hand, that's X-axis, and you are going to stretch it from X. Okay, it's horizontal, the X-axis horizontal, stretch it from X-axis. So actually you're moving up or down. Okay, you're moving up or down. So this point or any point, I pick a random point, any point on y equals to square root of x, you are stretching it up or compress it down along this vertical direction. That's something we call from x-axis. Make sense? Okay, that means dilation. Okay, now for example, I dilate by factor of 2. I want to times it by 2. I want to make it twice as large as before. It becomes 1, 2. Okay? And just like I said in translation section, transformation of graph basically consists of infinite many pairs of coordinate transformation. You can imagine there are so many points on this graph, a whole lot of points on the graph. You times it by 2 for every single one of them. Then your graph becomes something like that, right? You are timing all the points by 2, and the original red line now become the blue line. This is something we call dilation from x-axis. Okay. Another kind of transformation we call the dilation from y-axis. So sometime we're going to stretch my graph in a horizontal direction. Imagine this is the y-axis, this is the y-axis. You are stretching and extending your graph horizontally. You are stretching, hold your hand on the graph, you stretch it from y. So this horizontal movement is something we call that from y. Yeah. Now, that means this 1, 1, same graph, square root of x. If I stretch it horizontally, this direction, we call that dilation from y. All right. Now, for example, sometime I want to dilate it by a factor of 2. I want to time all the coordinate by 2. I want to time it by 2. Before it's 1, 1. Now I want to times it by 2. I want to make it as twice as large as before. That becomes 2, 1. Then infinite many these kind of pairs of coordinates, it makes my red line transformed into green line. And this is an example of dilation from y-axis. Okay, this is definition. But it's too tedious to go through this definition every single time. So instead, I summarize that in a coordinate form. Now, when we describe dilation, there's one thing that everybody usually make mistakes of. That's the value of A. So the dilation factor, formally the definition of dilation factor must be a positive constant. Must be a positive constant. It must be positive. It cannot be negative. Negative now become reflection. We'll talk about it later. So dilation must be something about a value, and it must be a positive value, and we call that a dilation factor. Now, if we move from x, then from the graph, we see that when you dilate from x, these two coordinate 1, 1, 1, 2, because you're stretching up and down, the x value does not change. The x value does not change. It's actually the y value being transformed up and down. So only y value will be affected if the dilation is from x-axis. So simply put, you can remember from x, change y. Yeah, it's the y coordinate being changed. So I dilate by a, then my coordinate y will be times by a. This is dilation. Then y dash equals to ay. Similarly, a dilation of vector from y-axis, that becomes something like this. When you move it horizontally, you're changing the value of x. You're dilating the value of x coordinate, not y coordinate. Right, so we can now describe that. If we're doing a dilation from y, and we now change x. The x coordinate now becomes ax, and now x dash can be written as ax. Okay, that's dilation. So dilation only change one coordinate, either x or y, if you just do one dilation. If you have two dilations, then obviously you just do quite a few steps together. Now, notation of reflections. Reflection is not a story. Now, reflection. There are also two kinds of reflections. First, reflection in x-axis. So reflection you can consider like this. Reflection means you're putting your equation in a mirror, and you're going to find your image in the mirror. And what does that look like? And what is the position of your image in the mirror? And the axis will now become the position of the mirror, where you place it. Yeah, let's go. Reflection X. For example, you are actually placing, imagine this whole x-axis, x-axis. I just label that. You place a mirror there, and there's a graph called y equals square root of x. By looking into the mirror, 4, 2 now have the image in the mirror. That's 4, -2. They are symmetrical about the mirror x-axis. And imagine you do the same thing for all the coordinates on this graph. Every single one of them, you find their pair in the mirror. And then you have the graph, which is y equals to negative square root of x. That's the end result of the reflection in x-axis. Okay? Similarly, reflection in y-axis, now you're placing a mirror at a position of y-axis. For example, this vertical line in the middle of the screen. That's where you put the mirror. The original function in red will now be reflected left and right. And now it becomes y equals to negative square root of negative x, right? Imagine there are infinite many coordinates there, and you're going to reflect it horizontally to the left, and they become the coordinates on the green line. And that's something we call reflection in y-axis. Okay. Now, summarize the change of coordinate. If we reflect in x, that's this example. When you reflect in x, say the coordinate 4, 2, 4, -2. The x value does not change because you're reflecting the values up and down. So 4, 2 become 4, -2. You're changing the y value. So very similar to dilation. So reflection in x will result something we call change y. See, the y coordinate now become negative. Reflect in y will now become change x. If you look at that in graph, 4, 2 become negative 4, 2. You change the value of x coordinate. Okay. So this is why we put reflection dilation together and put transformation separately. Transformation, you do something to the x, x will change. You do something to the y, y will change. But dilation transformation, in the language, it may be something we do to x and y, but the end result to the coordinate is actually the other way around. And this is also very easy to make mistakes. Let's have a look at an example. So when we have a graph, something we call y equals to 1 over x squared, and we're going to do the following transformations to that. Part 1. If you do want to have a go, you know the method we learned from translation, and you know exactly what to do. Try it first. Use your own time. Pause here, 5 minutes, then come back later. Okay? Now, part A, dilation by a factor of 4 from y-axis. By definition, from y means I change x. So the x value now will be times by 4. Y does not change. And now x dash equals to 4x. This is x dash. And y dash will equals to y. Remember, do not forget to rearrange it to make x, 1, y the subject, to make x and y the subject, because the original function, they're always something to do with x and y. There's no information about x dash and y dash. Okay, there's no information about x dash and y dash. So x equals to a quarter x dash, y equals to y dash. Now, you can now substitute into the original function, y equals to 1 over x squared. Now, y is just y dash, and x squared is just 1 over 4, x whole thing squared, and everything 1 over that much, right? And simplify, y dash equals to 1 over 16x squared and 1 over everything, time everything by 16, that's 16 over x squared, dash, sorry. But anyway, your result, when you answer the question, you're gonna remove the dash. And that's the final answer for part A. And part B, dilation by a factor of 4 from x-axis. This time, it's a different story because it's from x, so part B. From x, we know it means change y, x comma for y, x dash equals to x, y dash equals to 4y, x equals to x dash, and y equals to divide everything by 4, a quarter y dash. And now y equals to 1 over x squared, y equals to a quarter y, x just equals to x dash. And that means I time everything by 4, y dash equals to 4 over x dash squared. And you replace all the dash with the normal x and y letter, y equals to 4 over x squared. And that's the answer. Okay. And part C, reflect in x, that means we change y, x comma y. Reflect in x, that means I change y become negative. Then x dash equals to x, y dash equals to negative y, x equals to x dash, y equals to negative y dash. Then y equals to 1 over x squared. Then negative y dash equals to 1 over x dash squared. Then I time everything by negative 1, y dash equals to negative x dash squared, and 1 over that. And write down the final solution, y equals to negative 1 over x squared. And that's the answer. And part D, reflect in y. In y means change x. So x comma y, change x, that means negative x, comma y. Then x dash equals to negative x, y dash equals to y, and x now equals negative x dash, y equals to y dash. Then y equals to 1 over x squared. I replace x and y by y dash x dash. Y dash equals to 1 over. Notice that, be careful, this time we replace the whole x by negative x. So it's not just x being squared, it's the negative x dash. The whole thing represents for x, the whole thing will be then raised to the power of 2. So it's bracket squared. And y dash equals to 1 over 2 negative, make it positive, x dash squared. Then the final answer should be y equals to 1 over x squared. See, this example is a perfect example to show you that the dilation, reflection, all the factors are the same, just by changing the language. Sometimes from x, sometimes from y. The direction of transformation is so important that will actually make your end result differ to each other. They are very different to each other, just because the direction of transformation are the same, are not the same, are different. All right. And that's the end of part 1. In part 2, we're going to talk about the combination of transformations, how to find the equation of the graph after a combination of series of transformations. Thanks for watching and see you next time.